Okay. So let's wait for another 5 minutes. Okay, let's start our class. So can anyone tell me what have you done last week? Anyone? Okay, let me randomly point someone to answer my question. Lim Wan Yang, are you here, Lim Wan Yang?
Yes, sir.
Yes, what have we learned last week? Mr. Lim? Hey, Mr. Lim Wan Yang, are you here? Should I be saying? Okay, so last week we have learned about the three rules of the quantum mechanics. So let's Lim Wan Yang. What are the first rules of the quantum mechanic? Can you answer me? Or you are just looking for the answer? Okay. The first one is the principle of the energy quanta. Of energy quanta. So what are the formula commonly used in this energy quanta? this first principle? Liman Yang? Okay, can you tell me the formula that we commonly use in this first principle? E equals to what? Okay, the chef, fair enough. Okay, so let's go to the second rules. Kwa Yi Han, are you here, Kwa Yi Han? Mr. Kwa, what are the second rules? Okay, wave particle duality. Principle, yep. But what are the common formula that we have used in these rules? Under this, yes, Mr. Kwa, what are the formula? There are some formula we use to do it. Yeah, lambda equals to P equals to H over lambda, then P equals to mv. And at the same time, we also can calculate the kinetic energy, half mv squared. Third rules, what are the third rules? Okay, let me pick someone to answer this. Chua Yu Yang, are you here? Chua Yu Yang. What are the third rules? Yes, it's the uncertainty principles. Principle. Then what are the formula that we use inside here? There are two formula, okay? In this formula, we're saying that the location, the momentum are uncertain, or even the energy or the time are uncertain. So tell me the first one. Yep, delta P and delta S is more than equals to reduced Planck constant. This is the Planck constant divided by 2 pi. What about the second one? Yep, delta E and delta T is more than equals to reduced H. Okay, don't forget, we always deal with the reduced H. Okay, so basically these all three are the basic thing that we need to know when we're dealing with all the quantum mechanics. Okay, so whenever we talk about the electron, all these things are actually dealing with the electron. Because electrons are too small for us, so we need to get out of the way to measure it. So that's why we need all these three items, these three rules. Okay, let me recap a bit about the physics. So imagine that here's an atom. Atom will have a nucleus, proton, electron, right? So in the middle, we know there is a nucleus. Then the first orbit. How many electrons should be in the first orbit? Can anyone tell me the answer? Any guess? How many electrons? Yup, 2 electrons. Fair enough. Second orbit, 8. Fair enough. Third orbit, 8. Yep, we commonly know that as 8. But it can occupy to mostly 16 electrons. By common practice, we know that it's 8. So this thing we learn it in the chemistry or even the physics. So silicon, how many electrons does it have? Anyone? Not 7. Any other answer? Okay, maybe I create a poll, then let you guys see how many of you think it's a 14. Okay, let's create a poll to see how many of you think it's a 14 or 7. How many upper? Seven, 14, 28. Auto allow on what does it mean? Always like this. What happened? Sorry for the error. We launch it. Okay, let's work. See how many of you think it's a 14 or 18. 28. Okay. Seems like everyone have a standard answer, which you think is a 14 electron. Right. Okay. So we all know that the electron will be having the 14 electron. This thing everyone should have known that from a during the very last time during the high school study. Yes. So right now we are dealing with the 14 electron in the silicon. Okay. But in the electron of one atom, okay, there's one rule saying that every electron must move differently. RENTLY. Okay, even though you're under the same atom. Okay, for example, this one, the orbit, you have the electron 1, electron 2. So both these electrons must have moved differently. Maybe one moving in this direction, another one moving in this direction. Okay, or maybe one is spinning in this way, another one is spinning in this way. So actually electron is moving, okay? But maybe it keeps spinning and moving. But maybe the other one is spinning in the other way around and moving. So this one is two different action. So there's one rule saying that every electron must move differently. But how can we define their movement? How can we know what is their movement? Okay. So in order for us to know that how to decide their movement, there are 4 criteria. All these 4 criteria we decide as a quantum number. Okay, which is related to the lecture by today, quantum number. Okay, just a fast disclaimer. The slide is for the educational purpose only, and all the materials, all the equation, all the images are obtained from the following source. Okay, last lecture, we learned about how the electron behave under the quantum mechanics. So we also know about the location is uncertain. So that's why we know that we got it as we got the probability density function. And then right now, we are going to learn how the energy form. So back to this just now. For electron, as long as it is moving, there must be energy. Just like what we learned last time, there must be the kinetic energy for them to move. Okay, if no energy, then electron will not moving. Okay, back to this. Just now we mentioned that every electron must move differently. But how do they decide how they move? So this is the lecture that we mentioned today. So there are something we call as a quantum state of a quantum number of the state. What is this about? So basically, this one is the one describe the size, shape, and the orientation of the orbital of an atom. So there are 4 quantum numbers are needed. The first one, energy. Then angular momentum. We know that when the electron is moving here, they must be having some momentum. So also the magnetic force and also the spin. The spin, like I said just now, whenever it is spinning. Either it's spinning in this direction or spinning the direction. Okay, so this energy, we tend to measure it inside the integer. Maybe energy level 1, energy level 2, energy level 3, until maybe you don't know what. Angular momentum from the 0 to n minus 1. Then this way is the from negative to positive value. Okay, because this one, when you move in this way, the momentum will be in this way. But when you move in this way, the momentum will be in this way. So we define it as a negative and positive. Okay, so there must be some value. But in this case, we will put it as an integer. Then the spin, only 2. Positive half and negative half. So based on all this value, it will decide how the electron move. How can we say that? Just for example, imagine that. So we have a, let's say, nucleus, first orbit, second orbit, and third orbit. Okay, first orbit, n equals to 1, second orbit, n equals to 2, third orbit, n equals to 3. N is the energy level. Okay, inside you have the energy level 1. We call it as a principal quantum number normally. Then this one, energy level 2, energy level 3. Quantum number 1, quantum number 2, quantum number 3. Okay, in the first orbit, there has to be 2 electrons, right? 1 or 2. Okay, so in this case, both electrons must have moved differently. Then how to decide whether it's moved differently or not differently? Okay, the angular momentum can be 0. Magnetic moment can be 0, which means that these 2 electrons will be having the same energy level, same angular momentum, and same magnetic moment. But according to the rule that I stated now, every electron must have moved differently. So one criteria for them to move differently is the spin number, which is 0.5 and negative 0.5, which means that one is spinning in this way, another one is spinning in this way. So here all are the same. So you can see here are the 2 electrons. So which means that in this orbit, they must be having 2 electrons. Okay, but in the number of the electron in the silicon, the first orbit must be having the 2 electrons also. Okay, this one no problem. Okay, what about second orbit? So second orbit actually it can divide into two levels. Okay, spin number 0.5, negative 0.5, 0.5, negative 0.5. Okay, the first one, first level, it can also occupy 2 electrons. The remaining are the same. So these 2 electrons will be having the same quantum energy level, same angular, and same magnetic. So here can put 2 electrons. But the second level of the orbit, we still have another design info, okay, design criteria. which is the magnetic moment. You can see that every time we will change the spin number first. Okay. After that, we change the magnetic moment. So right now, magnetic moment, they have three different magnetic moment. 3 multiplied by 2 equal to 6. Okay. 2 plus 6 will be equals to 8 electron, which means that in this second level, we will be having 8 electron. And this 8 electron will be having the different movement. Imagine that this second orbit actually has a two level. Okay, maybe the first orbit has 1 level, third orbit have a 3 level. Okay, so first orbit having 2 electron, second orbit 2 electron at the first level, then 6 electron on the second level. Okay, and then third orbit also the same. First level 2, second level 6, 2, 3, 4, 5, 6. Then third level, okay, we can change this. Okay, this one 2, 5, okay, it's a 10. Okay, so total actually this one you can occupy about 18. But we normally deal with 8. 8 is more than enough. Then for the silicon, it has a 4 electron only. In this state, can you understand? Any question? But actually, this one is less important, I would say. The more important is the next slide. Any questions so far? Okay, if no question, then I proceed to the next one. So there's one thing. Okay, this time we just mentioning everything about the one electron, one atom only. Okay, imagine you have a 2 atom. Okay, atom 1 and atom 2. And the electron, the movement are the same for these two. What does it mean both are the same? Which means that both of these atoms are following this criteria. At first change the spin number, then second one change the momentum, change the spin number, change the momentum, change the angular momentum, something like that. Okay? So both atoms are the same. Imagine if these two atoms are getting closer and closer together. Okay? Closer and closer together. Then eventually both atoms will be intersect with each other. Maybe something like this. Something like this. Okay? So if both atoms are intersect together, which means that both of the electrons will be intersect together also. Okay, but according to the rules that I mentioned just now, all electrons must have moved differently. Imagine that if you have, let's say, second orbit, say this. Okay, imagine you have a second orbit, this one, the first rows. Okay, so this one is principal quantum number 2, angular momentum 0, magnetic momentum 0, spin number maybe 0.5, 0.5. So imagine that you have the, let's say, this one, first orbit, second orbit. And this second orbit and this second orbit intersect together. But both of the orbit are having the same movement. And according to the laws that I mentioned just now, electron cannot be having the identical movement. So what will they do? Okay, let's see this. So there's one guy, he called as a Pauli exclusion principle. This guy saying that in any given system, an atom, molecule or the crystal, no two electrons may have occupied the same quantum state. So in the atom, the exclusion principle means that no electron have same quantum number. So what can they do? If they have the same quantum number, eventually, let's say, even the same energy number, let's say E equals to M1, M1, E equals to N2, M1 both are also having the same M1. Electron 1, electron 2. So when they intersect together, they won't change the remaining quantum number first. Instead, they will forcefully create another two layer of the energy level, split into M1 and M2. And then in this case, when two electrons are having the same quantum level, for example, the same orbit, same quantum number, same situation, same movement, the first thing they want to make everything different is the energy level. They will split into two energy levels. Imagine if you have many electrons, let's say in, I don't know, orbit 32 or orbit 36, there are a lot of electrons. So when they intersect together, then the energy will keep on splitting, split until it forms a big gap. Okay, inside this gap actually is a M1, N2, N3 until Ni, something like that. Okay, in this situation, they will form a gap. Okay, let's say if the item or if the crystal are the, let's say, semiconductor, it will form two gaps. Okay, it forms something like this. So the first one is the conduction band. The second one is the valence band. So every time when we are talking about the conduction band and valence band, actually it is constructed by a bunch of the energy level. All these are energy level. Above there also, all are energy level. So back to this picture. Originally, when there are two orbits intersect together, it will forcefully create another two layers, M1 and M2. But if there are tons of the electrons coming together, it will form a band, which is a conduction band, valence band, and in between, we call it as a forbidden band. Okay, which means in this area, there won't be any electron occupied in this. But in this and in this, yes, there's an electron, something around inside there. Okay, in this part, any question? If no, type a no in the chat box. What is the difference between conduction band and the valence band? Is there a question? Okay, later I will explain this before I go into the next slide. Okay, so any question first for this part? If no, then type a no, so that I can know your response, other than just them only. Wang Chongyi, energy level has a more level. Because you can see that from M1 to the Ni, actually the construct of the many level. But when we make all this level together, we call it as a big gap. Actually, inside here is a discrete level, many discrete level. Wang Chongyi, can you understand this? Okay, any other question? So just now when your friends asking that what are the differences between the valence band and the conduction band. So let's see this. Okay, let me go here. So valence band is an energy band which is formed by grouping the range of the energy level of the valence electron, outermost orbit electron. The electrons present in the valence band are loosely bound to the nucleus of the atom, which means that in a semiconductor, basically there are two things. One is the valence band, one is the conduction band. Okay, so this is a conduction band, valence band. So normally the electron will be somewhere around here. All the electrons are somewhere around here. Okay, if you didn't receive energy, all the valence band will be staying in here. But if you provide the energy, provide heat, or provide temperature, then the electron will start getting the energy. It will jump to the conduction band. So when they jump to the conduction band, it will be giving you the electricity in the semiconductor. Okay. So just now when Lau looking saying there was a difference. At first, valence band, if you didn't provide anything, all the electrons will stay in quite in here. But all it had a loosely bound. Okay. Then what about conduction band? The conduction band is the band energy which is formed by grouping a range of energy level free electron. Free electron means that it starts to be conducting electricity. So at first, the conduction band is actually the empty one, okay? Because if without any energy, there won't be any electron jumping from the valence band to the conduction band. It won't be any. But if you provide some energy there, external energy applied, then the valence band will be jumped to the conduction band. Okay, so this concept. So electron in the conduction band have a higher energy than the electron in the valence band. You can imagine that the energy actually keep increasing. Okay, maybe this is in this level is a E1, E2, maybe E3, E4. Okay, E4 higher than E3, higher than E2, higher than E1. This is the concept. Then in between, there won't be any electrons staying in here because he will jump over here because there's no energy, no allowed energy state. Theoretically, there's nothing in here. Okay, but this thing will decide the width of this energy gap because there's an energy gap normally. It will decide whether it's a semiconductor, insulator, or the conductors. Okay, so Lau Lộc Jing, have I answered you the question just now? Okay, let me drink water together. Okay, so this is the formation of the energy band that I have mentioned just now. So when solid are brought together, so it will be the interaction between the electrons between the atoms. So there are proper balance between the forces. So the change will occur in the energy level, which is the energy gap, which may relate to the question by Wong Chung Yi. So when two atoms are brought close together, it will lead to the intermixing electron, then it will form the energy gap. Okay, this is what I mentioned just now. So very easy. Conduction band, valence band, in between, energy gap. Okay, electron jumping from here to here. So when electron jumping from here to here, you can see electron are here, but here it will construct a hole. Imagine that at first, here the hole are filled, but somehow if your electron jumping from here to here, you will create something like this because the electron already jump. Okay, so hole are there conceptually. Okay, so this is I will think this is an illustration of the energy that I mentioned just now. Okay, when you're getting close together, it will split into the two levels. So you can see that this is a graph of the interatomic distance. So when your distance is going further and further, okay, both electron will be having the same energy. But if your electron is getting closer and closer, so it will split into the two different levels or maybe multi-different levels. In this case, inside actually is not like this. Maybe line one. Okay, something like this. But if you're getting more and more electron getting closer, so it will seem getting more and more until it looks become continuous. Actually, inside there all are the discrete one. Okay, so this one is the Pauli exclusion principle state, saying that the joining atom will form a crystal does not alter the total number of the quantum, but no electron have the same quantum, so you can only split the energy level. So whenever when you're getting closer and closer together, the energy level will be split. So because we are going to form a crystal, okay, in order for us to form a crystal, we need to have a lot of the atom. Just like the first lecture, last time when we're saying a single cubic atom, we already have a 8 atom. Okay, just remember that. Imagine that a crystal, maybe a very small crystal, is the maybe 10,000 of the atom, 10,000 of the simple cubic. Imagine that. So that's why you can see that that's where energy get is from because of this issue. Okay lah. So this is the splitting of the three energy state, M1, N2, N3. This M1, N2, N3 actually represent this, the first quantum number. Okay, M1, N2, N3. Okay. So this one is not that important. Okay, the important one is this one. So visualization of a hole. So when the electron is moving, the hole is also generated. Okay. Imagine that originally, let's say electron are here, and here's a hole, here's a hole. Okay, let me draw somewhere around here. Okay, maybe this. So original is full, and this is a hole. Then somehow electron jump to here, to here. Okay, so right now here generate a hole. Here is a full. Let's say if this is a hole, we empty it. Okay. So let's say in the third level, here, jump into here. So here is a hole, here is a hole, then full. You can see that actually the whole macam keep on moving in this direction. Okay, moving to here. Originally here, then here is here. So somehow people will say that why is there a hole moving or the electron moving? Because when your hole is moving, it makes you look like the electron is also moving. So that's why people are saying that the hole is also moving. Actually it's a electron moving, but it makes it look like the hole is moving. Okay, this one, can you understand this? Okay, if not, then I skip for the next one. Okay, so this is a drift current density. Actually, drift current density is the measure of the electron, but this one we will discuss in the, I think, lecture 6. Okay, this one not important here at this moment, but we will soon deal with it later. So don't worry about this first. So you might be wondering what are the difference between the metal, insulator, or the semiconductor. Okay, imagine this is an insulator. So it also have the conduction band, also have the valence band. But the insulator, one of the key important one is the energy gap is very big. Okay, big until the electron here cannot move to here. Because it's too big, then you need to provide a lot of energy. And your energy provide is insufficient, no matter how big energy you give him, because the energy gap is too big. Okay, something like this. Okay, it moves into a very, let's say, big valence band. Okay, so this Eg is very large until your electron not even have a chance to move to there, no matter how much energy you provide to it. Okay, then semiconductor, it will be closer valence band. So the electron here, it can move when provided the energy. Okay, and then the metal or the conductor. somehow the conduction band and the valence band will be overlap with each other. So that's why somehow the electron can move freely. So that's why when you are saying the metal is a very good conductor, okay, because the electron will keep on moving from here to here, from here to here, from here to here. But why do we still need the semiconductor? Why not be using the metal to be our electrical component? Can anyone? Any guess? Why we don't act as a switch? Yes, somebody saying this. Any other answer? What do you think? Why do we need semiconductor? Any guess? 参虚片. But why don't we use the metal as our semiconductor? Control electron. So Yan Chang, your answer seems interesting. Can you explain more about this? How do we control the electron? Why do we need to control the electron? Why not we just let the electron flow? Okay, any other guess? Okay, let me pick other guy. Teo Yisi. Okay, we let other friend to answer the question also. Teo Yisi, what do you think? Why do we need the semiconductor? Why not just all using the metal? Apa BJT? Why do we need BJT? BJT is a semiconductor, I know that. But why do we need BJT? Why do we need semiconductor? Why not we use the metal to help us to do everything? To control electric. Okay. Any other answer? Okay, let's see. This is kind of open-ended, but there are some standard answers. Teo Leong Ho, are you here? Okay. Teo Leong Ho could give a very good answer, I would say. Actually, all of you are getting the point, I would say. Okay, so metal. Okay, we know that metal is a very good semiconductor, but we can't let the electron or electric to keep on moving 24/7. Okay, in some circumstances, we need to limit out the electron so that we can save the cost. Okay, in the engineering, everything are cost saving. Remember this. So metal, we know the metal is a very good conductor, but we cannot just let the electric to keep on flowing in the 24/7. So we need to do something to control it. So one of the good things to control it is to use the semiconductor. When we need to use it, then we only provide the energy, then it will become to work or to function. Okay, just like what your friend say, we have a semiconductor so that we can control the electron flow. Or like Wang Chungyi say, we can program the electron. Why do we need to program the electron? Because when we want them to do some necessary or some specific task, so we can use a semiconductor. Yes, semiconductor, we can do that. But if you want the method to do the specific task, it's very hard. Okay, so that's why semiconductor is a very important one. And if normally metal will be implemented in all the copper wire. Okay, if you know that. Let's say the LAN cable, then maybe the electric circuit, actually all are in the copper because this is a very good conductor. And let's say if you want to provide some of the resistance, then we need the semiconductor. If you want it to be a switch, or maybe some of a friend like to be a BJT, so this is a semiconductor. So that's why semiconductor is getting hotter and hotter nowadays. But of course, there are some big company in Malaysia, which is doing the semiconductor. For example, like Penta, or maybe the Unisem, or some of you doing the grid tech. Some of you may not know that, or one of the famous one we trust. Okay, all these are the semiconductor firm, but all of them are working in a different aspect. Some of them is inspecting whether the semiconductor has a defect or not. Some of them is to do with the molding. So different thing. Okay, it's a very interesting um study, I would say. So in this stage, any question? If you are doing some investment, you may know this kind of company. Any questions so far? Okay, so let's proceed to the next slide. Okay, so after having the gap of the energy, conduction band, valence band. So right now, we need to measure that how big is the gap, or how big is the gap. Now I want you saying that is there a single level? No, there's no single level, there are multiple levels. But we need to have some measurement to see that how big is the gap. But how are we going to measure the gap? So one way to measure is the density. So last time we know about the, let's say the volume lah, area lah, we learn the density lah. But we also can learn about the density in the state function. Okay, which means the density of this gap and this gap. And there are some formula. Okay, excuse me. There are some formula that we can always utilize in this case. Okay, this formula, if it didn't state anything, generally it can write into this way. G equals to 4 pi 2m 3 to the power 2 Planck constant squared E. Okay, m is the mass of either proton or electron, depends on the question asked. Then E is the energy level. You might be wondering, how are we going to use this? So normally the question will ask you to do something in this way. Okay, this one, yep, this one. It asks, consider the density of the state for the free electron given by the equation. Calculate the density of the state per unit volume with energy between the 0 and 1 eV. So in order for you to do this, you need to do the integration. N equals to integrate G dE. So in between 0 and 1 E, 0 and 1 eV. Okay, then we keep on doing this. We do the integration. 1 eV, 0, 4 pi 2m 3 to the power 2 is 3. Then square root E dE. Okay, in this case, we all know that this part will be treated as a constant. We just need to take this thing out. 4 pi 2m 3 over 2 to the power 3 1 eV 0 E half dE. And then keep doing this. 4 pi. Okay, we write as A, pretty mafan. Okay, and then this one. E given plus 1, 3 to the power 2. Then multiply by 2 to the power 3. Then this one will be 1 eV and then 0. Okay, then we keep on doing this. 2 over 3, 4 pi 2m 3 over 2, 3. Then this one is 1, 0. So we know that this is a 1 eV. 1 times 1.6 times 10 to the power 19, 3 to the power 2. Okay, so in this case, what is M and what is H? This one is a Planck constant. N 9.11 times 10 to the power negative 31. Okay. All you need to do is to replace every single value inside there, then you can get the final answer. So this is the way when we do it. Okay, maybe you can try another. Okay, let's say if I want you to do something like this, find the density of the state per unit per volume in between, let's say 1 eV and 2 eV. Let's calculate this. Okay, it's up to you now. Okay, are you able to get answer for this question? Anyone? Okay, let me pick someone to answer the question. Ko Boon Kyung, have you done the question? Math error. Okay. What about the rest? Can you get something or you get math error? So if you get the math error, you try to divide this thing divided by h 3 times instead of h to the power 3. Try to divide this thing by 3 times instead of just directly putting things inside there. So see whether you can get math error or not. Introducing. So if you can get any answer, just type your answer here. One point oh six times 10 to the power 56. What about the rest? let's wait for the rest of the answer and see how. But for me, my answer is different than yours. No, my answer is from 2 to 1 eV, 1 to 2 eV. The question asked is from 2 to 1 eV. Okay, if you can get any answer, just type there. We'll verify. Or you still get the math error. Okay, looks like we are having some different various answer right now. Okay, let's see. What else? Next one. Same as 1.28 times 10 to the power 20, 10 to the power 28. Okay, this is a very interesting. Looks like everyone will get the different answer. Okay, let's see your A. What do you get for the A? I mean the A is the one in front. This one. This whole thing. From here to here. What do you get for this value first? Your A is different than mine. The rest of you, what do you get for the A? Seven 0.086. Interesting. Means the one that I got having some error here. Let me check. 3/2. 1.5. Interesting. Okay, all get 7.06. Let me try my side here. Okay, I retype everything. 4 multiplied by math pi and multiplied by 2 multiplied by m to the power 1.5, which I have a bracket here, and divided by with the power of 3. This one divided by 3, 5. Let's see. Okay, my value, yep, correct. Just now some typo, I believe. 7.085 10 to the power 55. Then your answer is 8.29 times 10 to the power 27. Do you get the same answer as me? This one. 8.29 times 10 to the power 27. Do you get the same as this? Okay, right now correct. Okay, sorry the mistake that I made. I believe it's if I'm not mistaken. Let's see. Yeah, I typo. That's my asterisk. So that's why everything different. Okay, we take a 5 minute short break, then we come back afterward. All right. Okay, shall we resume the class? Anyone, are you still here? Are you still here, everyone? Hello, if you are here, then tell me yes. Okay, all right. So let's continue our class. Okay, by the way, so tomorrow we'll be having our practical class. So please install the software first before we really go into the class. Okay. So just now when we talk about all the integration, everything, we are just using the one without any specific condition. What is the specific condition? Which means that we didn't say whether the electron is in the conduction band or the valence band. But what if the electron are in the conduction band or the valence band? This thing we need to consider. Okay. So let's say if there's an electron coming from here to here, so hole will be generated. So somehow in the conduction band that are starting having the electron, then the valence bands are having the hole. Okay. Then imagine that right now we are going to measure the density in the conduction band. But how are we going to do this? So right now, the formula is still the same. Just that we need to consider two things. EC and the M asterisk N. First thing, what's the EC? Okay, this is the conduction band and the valence band. The energy level here, we call it as a EC in this level. In this level, we call it as a EV, valence band energy and the conduction band energy. So in the conduction band, if the electron is somewhere around here, this energy level, okay, E. So formula are we going to use? So let's see. So imagine this GC E equals to 4 pi 2 M asterisk 3 H cube E minus EC. Okay, E minus EC is the energy level that I mentioned just now. E minus EC. But what about this M asterisk? So if the electron have jumped from the valence band to the conduction band, we need to use the effective mass when it is in the conduction band, which means that when it is free, the electron size will be 9.11 times 10 to the power negative something like negative 31. But if somehow if this electron move from the one band to another band, so the mass will be changed. In order for us to do the mass changes, we need to multiply a constant. So in this case, if it's the electron, we need to multiply by, zoom me first. We need to multiply by 1.08 if the thing is in the silicon. So you can see that there are few rows here, few columns here. Silicon, this one is the gallium, arsenide, and the germanium. So in this case, let's see, MdN, MO. NO means is the 9.11 times 10 to the power 31, original one. So in order for you to calculate the effective mass, Mn, asterisk, you need to use 1.08 multiplied by MO, which is 1.8 multiplied by MO. If the case is for the hole, you need to use MO, which is the hole, the mass of the proton, multiplied by 0.56. Okay, this is the concept. Then one interesting, you can see that your E must be minus EC, because whenever when you jump from here to here, your E must be higher than EC. But let's say if there's a hole here, okay, then so you must be having a E somewhere around here. So your EV must be higher than E. So when we do the subtraction, we need to use the highest one, deduct the lowest one. Okay, then let's see how we're going to apply this in our question. Imagine if we had this question. Determine the number of the quantum state in the silicon between the EC and EC plus KT. Okay, in this case, we are going to use the electron. Okay, because this is the electron one. And then we can see that this is EC and EC plus KT. Okay, how are we going to do this? So let's see. So in order for us to do this, everything looks normal. 4 pi 2m x-ray n 3/2 h cubed E minus EC. We also do the integration. Right now it's a EC plus KT and EC. Remember, we might use put the highest one to the top, lower one in the bottom, and equals to 4 pi 2mn asterisk. Then this is the 3/2 h cubed E minus EC. And then we just keep doing this. Hold this thing at a constant. 4 pi 2 multiplied by 1.08 multiplied by the MO, sorry. This one is a 9.11 times 10 to the power of negative 31, 3/2, then h cubed. And then we do this EC plus KT E squared E minus EC. Okay, same thing we did. We need to do the integration. So this one I put as A. So 2/3 A. Then this one is the E minus EC half then 3/2. Then this is the EC plus KT. It's a EC. Okay, and then in this case, we just replace this inside here. 2/3 A. EC plus KT minus EC. KT 3/2. Then this one is a minus 0. So we remain this only. Okay, in this case, since this thing you can measure in the EV, okay, KT. K is the Boltzmann constant, then T is the temperature. But E, we normally measure it in the EV. Then your KT can be equals to, we open back the slide 2, this one. We need the constant list in this case. Okay, zoom it. Okay, Boltzmann constant. Mana Boltzmann constant saya? K. Okay, 1/38. 1.38 times 10 to the power negative 3. Then your T. So in this case, let's see. Temperature at 300 K multiplied by 300. Okay. And then this thing, you keep on multiplying this, then you get 8.62 multiplied 10 to the power negative 5. Okay. Yeah, this one. Or maybe you can straight away multiply this because this one is in a EV form. Okay. And this thing, you can see that actually this thing is a 0.0259 multiplied by 1.6 times 10 to the power negative 19. Okay, so this one you can use the KT minus multiply this. This thing is in the Joule form. So let's see. I remove this. So imagine a K is 1.38 multiplied by 10 to the power of negative 23. Then t equals to 300. And let's say kt equals to k minus t. Okay, you can see that mana kt saya ada in kt. Okay, 4 by 139 times 10 to the power negative 21. Then you see the one inside there 0 by 0259 0 by 0259 multiplied by e. Oh, sorry. Yeah. Okay, you can see that both values are actually kind of similar. One is 4 by 13 times 10 to the power negative 21. One is 4 by 14 times 10 to the power negative 21. So that's why people tend to use 0 by 0259 to make it shorter. Okay, so back to the slide just now. You just need to multiply everything, then you get the final value. Okay, maybe let's try another example to make it more easier to understand. So let's see, this one is a free electron. Understand, we do the, let's see, EC 2KT, and then the EC. So this one is, okay, try to do B. We do B first, then see whether you can understand. I think I already sent you the link, right, for the lab. 1:30 to 3:30. I already sent the invitation, right? The lab is actually distributed into two groups. One is the odd week, one is the even week. You need to check your timetable. You are belong to which group. So for this question, I changed a little bit. I changed to EC. Yeah, plus 2 KD. Sorry. Very sorry. Typo. Plus 2 KD. So may I know what answer you get? Anyone done? So if you have done this, then you type your answer into the chat box. Okay, any answer? Lee Zerlin, are you here, Lee Zerlin? Okay. Okay, reasoning get the answer of 5.99 times 10 to the power 25. Okay, about 6.0 lah. What about the rest of you? Do you get the same answer as your friend? Anyone? What do you get for this question? Brenda, what about your answer? Okay. Any other answer? Okay, I believe it's the 5.9 or something. Or 6. Close to 6. Okay, so this is how we do it. Very simple only. So I think I will end the class for today. Any question? Then we only continue do some other question for the next class. Okay, so I will see you by tomorrow for those who are going to attend my class. Okay, thank you everyone and have a good day. Okay, bye everyone.